I've been living in South Carolina for the last 3 years, totally enjoying it after 20 years in California, which I enjoyed a lot after like many years in Russia. So now I'm here, I'm happy. And I was teaching logic, and that included Lambda Calculus, so I believe like I'm kind of familiar. I learned Lambda Calculus when I was told that I have to teach it. So I hope to like give the ideas to you, and I believe almost everybody here knows JavaScript. So I based the whole presentation on JavaScript, which is like a version of Lambda Calculus, although opinions may vary. So here's the list of topics that we are going to talk about. Lambda Calculus is the general, very generic theory of functions. But again, like, what are functions? Opinions also vary. So I'll show like the history, and then we'll see how, based on just plain functions, abstract functions, we can build everything up to like monads. Well, I'm not going into monads. So in the set theory, like 100 years ago, when set theory was totally, absolutely popular, and people expected that this thing, set theory, would be the paradise where the humanity, the mathematics, will stay forever. Well, actually it didn't happen, although Hilbert counted on it. So when you like learn it in school, you'll feel like this is a graph of a function. Well, what we see is a graph, not a function. So some things are actually not like doable in set theory, and some functions just cannot be calculated. One example is busy beaver. If you're familiar with Turing machines, busy beaver is a Turing machine that is like does as many steps as it can with a given number of states. So recently, I mean like last month probably, like, or last 2 months, it was discovered that busy beaver with just 5 states is the biggest busy beaver machine for which we can calculate the slowest. The machine that takes like the most steps. They also proved that busy beaver with 6 states, just its length cannot be calculated. So what can we do? Even if we have like set theory, no, it's not doable. More, you can easily define a function that cannot be expressed in set theory. So we had to do something. Like in the beginning of last century, people were kind of not sure, are even those things functions? But now we are all write code, and we know that we can write a function that we may not know how to express in set theory. And you can also see like definitions of function that Cameron Presley was presenting yesterday. So here are a couple of functions that you cannot represent in sets. Again, like I'll be using JavaScript all the time. So function f takes a parameter x and returns itself. How can you write it in set theory? Not in Gödel Bernays, not in Zermelo-Fraenkel, and you'll need maybe quines, but that's not the set theory that mathematicians would like to deal with. So, and I'll be using this like more modern coding style of JavaScript, which is like this. F is a function that takes an x and returns itself. Or like another function, h, which takes an x and returns x plus dot. So we can write like a load f, and h applies to itself. Well, no, neither function f, neither function h can be expressed, neither h of h can be expressed in set theory. So we will need something different, a different language. And the language was invented like after people were disappointed in set theory. It was invented by Moses Schoenfinkel. Well, a mathematician from Moscow. He was a little bit crazy, and basically he died in a madhouse, and all his papers were burned. So he may have invented a lot of stuff, but we don't know. But he shared his knowledge. He shared his knowledge with Alonzo Church. He shared his knowledge with Kari Haskell. So Haskell expanded this knowledge with combinators and so on. So Schoenfinkel invented this function that may take themselves as arguments. Alonzo Church formalized it and introduced a formal Lambda calculus. First it was typeless, then like 10 years later typed Lambda calculus, which I will not cover. Then John McCarthy invented Lisp, which is an implementation like implementation for those days of Lambda calculus. Then Brendan Eich invented, or rather re-implemented it in JavaScript. He called it LiveScript, but then for marketing purposes he called it JavaScript. Marketing people called it JavaScript. And then typed Lambda calculus. Well, is implemented in the shape of TypeScript, and it seems like everybody now is using TypeScript, right? Like everybody I hear around like TypeScript, cool, yeah. So, and this is Anders Hejlsberg, the guy who invented not Pascal, but Delphi, and he worked in Borland. I also worked in Borland, but we didn't intersect, unfortunately. But, well, because those were the days of Microsoft, so they just sent a limo, like they loaded Anders and took him over to, how called, Redmond, yeah. So, and they did it like with a bunch of other people from Borland. Okay, we were left alone. So, what's the language of Lambda? So, Lambda is a theory, meaning that it has a language and it has some rules. So, the language is this. Like on the left is how it looks in plain Lambda calculus, and in the middle is how we express it in JavaScript and what's the meaning of it. Like a variable, just any names. So, you could use Latin characters, you can use like, I don't know, Chinese characters. It depends on how you do it. M and N, in this case, they are just some expressions. In Lambda, they are called terms. In JavaScript, they're called expressions. And this means literally that we apply M to N. And we don't tell you what does it mean, apply. Later, like the rules will tell us what does it mean, this application. And abstraction. So we have an M. M may contain, like, it's an expression, right? So it's a combination, like parentheses, lambdas, whatever, arrows. And so it may contain X somewhere inside. So this is an expression that is built out of X and M. So that's it. Abstraction, application, and plain variables. And compose them. So that's it. You can write it in Lambda, you can write it in JavaScript. Like for a programmer, it's natural to write it JavaScript style and forget about Lambda character. Well, Lambda character was just introduced not because like Schoenfinkel loved Lambda. He didn't love to write all those circumflex, I believe they're called, over the characters when they type. Well, there were no computers there. They had to use the typewriter and then like draw all those circumflexes, and it was hard. So that's how Lambda appeared before expression, but we'll be doing it in JavaScript. So here are examples of Lambda expressions. So you can ignore or you can read that left column, but in the middle is this, JavaScript. Just a plain variable, or applying X to the result of applying Y to Z. Or we can say like apply Y to Z and apply X. Or we can say like take an X, apply Y to that X, and apply the result to Z. What does it mean apply? We don't know. And we'll show how we can like tweak it to transform one expression to another. Like have an expression X returns X and apply it to Z of T. To Z apply to T. Well, we probably know that X arrow X is just an identity function, but we don't have like any transformation that can tell us it's an identity. This is like more complicated, so we apply X to X, and we apply it again to X applied to X. And this is Y combinator, like a simpler form of Y combinator. So I'll show you how it works like a little bit later in the end. So combinators were invented by Moses Schoenfinkel, and basically here are examples of combinators. like, of course, there could be an infinity of combinators. Here are some important. I combinator, it's an identity, takes an x, return an x. Like I applied to any a will be equivalent to a. What that equivalence means, I'll talk about it later. So k combinator, take an x, then take a y, and produce an x. So it's like a constant function. It was like a while ago, it was my favorite interview question. Can you, like in JavaScript, write a function, in JavaScript or in Java, write a function that takes a value and returns a function that always returns that value? And if you're a JavaScript programmer, it's probably totally obvious. If you're a Java programmer, it's like it's a puzzle. How can we do it? How can we return a function? So different mentalities. So k combinator applied to a, right? So x, y, x applied to a will eventually have a function that takes anything and returns an a. K combinator applied to a and then applied to b. It will be a, whatever the b is. And S combinator, this is an important combinator that, like Java people, again, like Java people critiques of Java people replace with Hibernate, with Spring. Well, I'd say because they don't know what S combinator is. If you can write S combinators and if you can use them, you don't care about those springs. So S combinator takes x, y, and z and parameterizes x with z and y with z. So z serves like something like an environment. So we apply x to y, but both are parameterized. Like for example, S, we have two functions, f and g. So we parameterize f with z and we parameterize g with z and apply the first to the second. So we keep z as a as an environment. So, but again, what are these? What does it mean that it's equivalent? Actually, this works as a refactoring. So again, like Java people know what refactoring is. When they use like a good IDE, so they refactor, do like big refactoring, small refactorings. But frankly, I don't know if JavaScript people practice refactoring, but here are examples of refactoring. So this is the same picture, but with these equivalences, and they are refactoring. So I'll show you how do these refactorings work. So one refactoring is called, in Lambda Calculus, alpha equivalence. In refactoring, it's called rename a variable. So we have like one expression x, arrow x of something. And we rename variable x with y. So that's it. We just renamed it, hoping that, well, we have to check that y is not present in expr. Otherwise, it will be cheating. So make sure that you only rename free variables that are not like coming from outside. No, they're not used inside. Otherwise, you rename them inside. So another refactoring is called beta equivalence. And beta equivalence consists of like one way, it's called reduction. The other way is called abstraction. So in programming, it's called like introduce a variable or like extract a method. Introduce a method or extract a method. Beta reduction. Inline a variable, right? So we have an expression like x, arrow x of x, and if we apply it to a, we can do the substitution. Substitute x with a everywhere in expr. So, like in an IDE, in IntelliJ or whatever, IntelliJ it supports JavaScript, so it's called inline a variable. In this case, we inline the variable x. And in the opposite direction, beta abstraction. We had an expression depending on a, and we extract that a, and we have this function. So it's called, if you do refactoring, you have an expression that depends on something that is defined outside. And you do refactoring called introduce a method or introduce a function. And it will extract that function, and we'll have this function. This parenthesis is extra. So, like in this example, x, y, x, then y, and return a sum. So it can be represented as y arrow 2 plus y. So if we go this way, we do like inline a variable, we inline an x. If we go that way, we extract a method, introduce a method. Okay? So, and the other one, the third way of refactoring in Lambda Calculus is called eta equivalence. It may look like, if you see it the first time, it may look pretty similar to beta, but the difference is in beta, we substitute something that is there inside, like a expression depends on a. Here, we substitute with something that is not there. So x, if this expression doesn't actually contain any x, what's the point of having like arrow that calculates something but doesn't use the variable? We don't care, so we can replace it with just x. So we inline that function. That's refactoring. And we can go like in the opposite way, and again, like introduce a function. But we don't use this x, so we don't care what's inside. Just we introduce that function for some reason. We don't know why. We don't know what for. But we can do it. Because all those equivalences in Lambda Calculus, they are equivalences. That's why I use this. This is not exactly legal to use JavaScript equal, but I use it like with artistic purposes, just to represent things. Don't take it literally as like literal JavaScript. So now that we have this, what we can do there, except for like, refactorings and like applying functions and doing abstractions or whatever. We can start with logic. How can we represent logic? So we can define an expression like condition. So it takes a b, and we think that b is something like logic, some logical value, Boolean. But again, we don't use any types. JavaScript does have types, but runtime types, but we don't care about types. Condition takes a b, and then it also takes like one expression which will be called if b is true, another expression which will be called if when b is false, and it goes like this: apply b to the first, and apply b, and apply to the second. But b chooses which one to call, which expression to return, if true or if false. Now, how will true look like in this case? True takes two parameters, because like it represents a Boolean. It takes one parameter if true, another parameter if false. Oh, I can use my mouse cursor. So, and then return the value of the first expression. Well, because it's true, so it represents true. False, on the contrary, it takes if true and if false, and return the second value. So it's like both are functions that takes two expressions and return either the first or the second. So like if you think of them as something that takes a pair, so it's first projection and second projection. So now, okay, we have two Booleans, right? True and false. How can we represent Boolean connectives? And or not. We can start with not. So if x is a Boolean, how do we represent not x? We pass false to the first one and true to the second one. If we apply x to false and true, what will happen? If we apply to false, it will return true, because it returned the second. If we apply to false, if we apply to true, it will return false. So that's how it is. Like, if x is true, the result of this application will be false. If x is false, the result of application will be true. And so that's how AND works. So it takes two values, two Boolean values, x and y, and returns what? In the case x is true, it will return the other one. Why? Because we don't know like if y will false, so we'll need false. But if x is false, then it will return the second one, which we know is false. So that's how true and false return like a conjunction. True will choose y, false will choose itself. Or, on the contrary, we'll be choosing like, if we are good, if we have true, it will return true. If we are not good, if we have false, it will return the second one. So false will choose y. So if we have false and true, it will choose y, which is true. So okay, false or true is true. So that's how the whole logic, Boolean logic, can be represented here. Well, and there's more than one logic, like there's more than one Boolean logic, but this is a primitive two-valued Boolean logic. Okay, but not everything is Boolean. So we remember we defined not as x that takes an x and returns x applied to false and to true. That by definition. Now let's define like two funny values. F that takes an x and return not x applied to x. And then z, which applies f to itself. Now what? Z is what? Z is, let me move it here. Z takes an x and return not xx applied to f. Meaning we substitute x with f and we get not ff, but z is ff. So we see that z is actually a fixed point of not. So it's equivalent, it's not equal, but it's equivalent to not itself. Well, no, it's not a Boolean value, but not everything is Boolean like in the real world, right? Like that piece of paper in which on one side it's written, what's written on the other side is true, and what's written on the other side is false. We can do it in JavaScript. We can do it in Lambda Calculus. So now we have Booleans, we have logic, and we can have numbers. So how are numbers represented in Lambda Calculus? Numbers are just, numbers count the number that a function is applied for any function. So what does it mean that we apply a function 0 times? The first line. It means we don't apply it at all and we produce an identity. So this is the operation of applying a function 0 times. Applying function once, it's just like apply it once, right? Take a function and produce a function that takes an x and returns an f. We could refactor it into just f. So what is 2? 2 means apply function f twice. So take an f, and for any x, just apply f twice to that x. 3 meaning apply it thrice. I don't know if there is a, like, if Shakespeare invented the word for applying 4 times. Thrice is from what? From Macbeth, right? Thrice the brindle. So, and how do we apply like n times? If we have a way to apply a function n times, that is apply n to f, how do we apply it once more? Well, we basically apply function f again to that x. Well, this is wrong because x is missing, right? So x error. So this operation of like having an n and applying like a function to the result one more time is called next, or is called suc for like succeed. So n plus 1. So this is how Giuseppe Peano explained to the world how natural numbers can be expressed theoretically. Before it was like, oh, what's a number? It's like you take a set of something and then you calculate. Like you can model it by like add one more element, but again it's set theory. Can we have like numbers without that theory? So this is the way. This is the implementation of that way. Apply, like for any function, apply it n times. Now, okay, numbers, but what can we do with numbers? We can add, we can multiply, we can take power, and we can check if it's 0 or it's even. See how it is. Given n and m, how do we add them? Well, look at it like pragmatically. If you have a function, how do you apply that function n plus m times? You apply it n times and then m times. Or probably like in piano, axiomatics, probably in Lambda Calculus, you can do it the opposite way, like apply it m times and then n times. Commutativity can be proven. So how do we do n multiplied by m? Well, it means that we do f m times and do this operation, like applying m times, do this operation n times. So that's an easy, like an easy implementation of these two, of these two operations. Power is even easier. So when we do n m times, so it will mean that n will be applied to f m times, or mf, whatever. So that's how it works. So how do we check if a number is 0? Like, suppose you have only functions, right? How do you know that this number, this like number of operations is 0? Here's the trick. Take these two terms. One is takes a value and returns false, and the other one is true. So if we apply n 0 times to this function, well, what? We'll have an identity. An identity of true is true. So that's how it is. But if we apply it more than one time, we'll have this like apply x arrow false. So we'll have true arrow false. So we will have false. And every time like we apply it again and again and again, and we'll be always having false. So that's the cheap trick to see how the number is 0. So it will return true only like on the first application when n is not applied at all. Similarly, we can check a number for evenness. Should be not x. Let me edit it right away. Yeah, so if we don't apply n at all, if n is 0, we'll have true. N is even. Now, what if n equals to 1? So we apply not true, we pass true, and we apply not to it. We'll have false. Apply not again, we'll have true. So it will be alternating like not. We'll do as many nots as we have n. So if n is even, we'll have like an even number of nots, which is we'll have true. So we'll be flipping it like true and false n times. So these are numbers. We have logic. We have numbers. We can go further. We can introduce data structures. This one is already kind of familiar because we did this trick with Booleans, right? So apply like f and choose either the first or the second. Except that for a pair, the ideology is very different. What does pair do? It takes one value, like the first component. It takes another value, which is the second component. And basically, then we'll have this like entity that can be used to apply function f to the components of that entity. So f, a function that takes two values, two parameters, will be using the first component and the second component. So if we write like pair of x and y, so then apply that pair of x and y to an f, will amount to applying an f to both parameters. So this is what pair does if you implement it like in any way in programming. And since we have pair, we'll need the first projection and second projection. First projection, like we take a pair and apply true. What does true do? Remember that function. True returns the first component. So we take pair of x and y and apply it to true, it will be returning x. The same with the second, it will be returning y, because if we apply it to false. So, and also, like if we do it like first of p return the first component, this is the second component. So if we pair them again, we'll have the same pair. We'll have x and y, that's it. So now we have pair. If we have pairs, right, like remember, maybe you don't remember, like I don't, but how Lisp was built. Lisp was built on pairs. Like it was, I don't know, PDP, something like an ancient machine that has two registers. So that's car and CDR. So based on that, like built was Lisp to Lisp was built on that machine that has like luckily had this good structure, and basically it helped to build the whole Lambda Calculus, which was called Lisp. So now that we have pairs, how can we represent an option? Like imagine you just have like, if you forgot about Lambda, how would you represent an option? Option either has a value or not. So you'll need like you'll need a pair. The first is flag is empty. The second one is value. And you ignore the value if it's empty, but you don't ignore the value if it's not empty. So here are two ways, like two kinds of option. One kind is none, so nothing there. We'll have a pair with true and true. True means, oh, it's empty. Sum, which means we have an x. So we take an x and build a pair. Empty? No. And it will keep x. So, okay. So this is how we'll build a pair. It's like almost a value, but not guaranteed. What do we do to check if the pair is empty, if the option is empty? We're given like an option, so this is something that is a pair, that is an option. And we take the first component. The first component is true when it's none. So it's empty if we apply it to none, and if it's not empty if it's applied to something else, like to sum. Again, you can apply it like is empty to any value, but you will get garbage. Well, because like garbage in, garbage out. But for options, it will work. So this is like an emptiness flag. And like, how many of you are familiar with flat map, map, filter, all those functional? Okay, so I'll cover this a little bit. So flat map means we have an option, xopt, and we have a function f that returns another option, like given a value. So how do we define flat map? And we'll need, given an option and a function, we'll need something that either none or another option. So what choices do we have? If x option is empty, so there's nothing to apply function to, so we'll return a none. But if it's not empty, we'll take this value inside, which is second component, and we'll apply function f to that. And f returns an option, like we expect it to return an option. We think that it returns an option. So if it's empty, we return none, otherwise we apply function f. So that's flat map. Like if we apply map, we'll have like an option of an option. To convert option of an option to a plain option, you will need flatten. I'm not defining it here. On the other hand, if we have like an optional value, and if we have a function that takes x and returns a y, like some whatever, so we'll do it a little bit differently. We check if this optional is empty. If it's empty, the result is none, like no value, no result. If it's not empty, so we apply f to that second component, to x inside, and we'll wrap it into sum. So we'll have an option. In Scala, you would say like option of it. Well, because Scala works on JVM, JVM has nulls, and so like keeping null in an option. But that's, well, the same with Java. I don't know if Java's optional like deals properly with nulls. So, but anyway, now we are in JavaScript, so we can be like ignorant regarding nulls. Null is just another value. So this is how it is, like take an option inside optional value, maybe x, maybe not, apply an f, and produce something that either f of that x or a none. And filter is yet another operation. Well, if you use TypeScript, I believe you deal with filter, right? I hope. Take an optional value and have a condition, and we check that value, like if it satisfies the condition. If there is a value and it satisfies the condition, we return that value again, wrapped in an option. But if not, in any other case, it's just none. So given an optional, given a condition, we check, is it empty? If it's empty, it's none. Does it satisfy the condition? If it satisfies the condition, okay. It's the same like thing that was inside that. That's the same option. Otherwise it's none. Yeah, I believe here we should have. We don't need to wrap like once more. Yeah, this is the right way. So if it satisfies the condition, then, oh my God, sorry. Like this. So if that x inside satisfies the condition, then we return the same optional, except otherwise we have none. That's the right expression. Okay, so that's option. We have like pair, we have option. But we have pair. We can build a list, right? Which is similar to option, except that the second value is also a list. So how do we represent the list? An empty list is called nil in functional programming. So it's a pair of true, again, like in option, meaning it's empty. And what's in the tail, we don't care, because like it just something. And we can also concatenate, like given a value, given a list, we build a new pair that says like, oh, it's not empty, and we keep a pair of x and the tail. The tail can be empty, the tail can be like a bigger list. It could have like linked forever, but we don't have mutability here. You cannot have a loop. I don't know, like of course, like in JavaScript you can have mutables, so you can have loops, but not in Lambda Calculus. So it will be like a list going maybe whatever, but it will stop somewhere because we only use these two operations, either nil or const. So it will be always like finite, unless our code runs infinitely, but we're not there yet. So what operations do we have on lists? So is empty. How do we check if the list is empty? This is the flag. So we take the first component. It says, yeah, if it's true, it means it's empty. What does it mean to get a head? So we take a list, and take the second component. Of course, if we're dealing with an empty list, so we'll be like kind of, we may have a problem, but again, it's not universal, like garbage in, garbage out, so that's the principle. So we take the second component, which is what? Which is this pair, head and tail. And we take that, the first component of that pair, which is the head. So this is the head of the list. And tail is here, excess. When we did concatenation, when we added a head to, when we added a head to a tail, so that's where tail is hiding. So we take the second of the second component. And similarly to what we had here with map, we can apply like given a list and apply f to all the elements and produce a list of results of application, f of x0, f of x1, and so on. So how do we do it? If access is empty, so we are there. We already have an empty list. Otherwise, we apply f to the head. So we concatenate, apply f to the head, which is this x, and do that application again, do that map with the tail. So you see, like having just functions and their applications, we defined a bunch of functional functionality in this JavaScript without like having to create libraries. These are the libraries. Of course, it's primitive, and in real life, maybe like we have to catch errors or whatever. So, okay. I'm not going further, like I'm not introducing trees or whatever, but you can figure out like how do we represent trees. Probably like you can have a list of lists, so like on each level have a list of trees, and so on. You can like reproduce any functional data type going this way. Now back to combinators. So what combinators do we have? Like we have many. So generally speaking, the whole Lambda calculus can be expressed using these three combinators, I, K, and S. So if we apply S to K and then apply to K again, actually you can check like at home that SKK is equivalent to I. You'll produce an identity. It's easy to check, but I'm not going there. So the question was like, can we leave S, K, and I were invented by Moses Schoenfinkel, but well, later it was discovered that S and K are enough. So I can be represented as a combination of S and K. Can we have just one combinator? And people started like looking around and inventing single base combinators. One of them is X. It is probably the simplest combinator. I believe there's like an infinite number of possible single base combinators. So X can be represented as X of S of K. If you want to represent X combinator without using S and K, you can just substitute the definitions of S and K inside, and it will have like a larger expression in lambda. That is just a lambda expression. So everything can be expressed through X, except that it's not much readable. So K combinator can be expressed as X applied to X applied to X applied to X. You can just like do it like for fun at home, like you don't need a JavaScript interpreter for that, but it's not hard. And S can be expressed as X applied to K, so we can write like X, like one more X, like 5 X's, and that will be S. So that's like a little bit of magic, but that's how it is. And the famous Y combinator, it looks like this, except that written this way, it will not work in JavaScript. It works in Lambda Calculus, but not in JavaScript, because you'll need lazy evaluation to use this form of Y combinator. So we can write that, but better like turn the expression lazy, and I'll show you in the next slide how to make it lazy. So like we take a function, And basically, this expression gives us a y combinator. What is y combinator good for? It can produce, for any function, it can produce its fixed point. Like, remember we saw a fixed point for not, like something that is not itself. So we can go further and have a fixed point for anything, like x equals to minus x and whatever. Well, that's 0, right? So we defined y like this. So if we apply this y to some f, what will we have? I renamed g to h, applying like rename a variable refactoring, or also known as alpha equivalence, so that we don't mix g and h here. So we have this y applied to f, meaning we do substitute it. So we removed f in this expression, and we applied beta transformation. So if we do this and substitute like g with h, we'll have what? We'll have an expression f of h, f of h of h, f of h of h. But we have this outside. So the thing outside pops out, so we'll have what? You see this thing? It's y combinator again. So we have f applied to y of f. So this magical, like pretty easy looking trick gives us a fixed point for a function f, of which we don't know about. Like, take a function, here's its fixed point. But probably, like, if you take a function like multiply by 2, what's a fixed point of multiply by 2? It's just another lambda expression. It's not a number. So what's a fixed point like, I don't know, plus 1? Another lambda expression. So lambda calculus like gives us more, because not everything in lambda is a piano number. Not everything is a Boolean value. It's just an expression. So like, how do you treat it? It's tricky. But again, like in other theories as well, when you extend like how like complex numbers were invented, people decided, okay, let's introduce this new entity. So similarly here, we can have like a fixed point for any function. It doesn't exist in like our specific theory, like not in piano numbers, not in Boolean logic, not in like real numbers, because I is not a real number. But we can extend the theory. So because we have a fixed point, this trick can be used. Well, see, we could also only write finite like expressions, right? But how can we do loops? There's more than one way to define loops by just applying functions. One method, I'm not covering it here, is U combinator. Well, like you can look it up, and it turns out that U combinator is like popularized by Utah State University. So I don't know how it's related. But it wasn't invented in Utah. So U is simpler, but here is like for being more generic, and because Y is more popular, so here how it is. Suppose we want to define factorial, right? So we can use recursion. But how do you define recursion if you can only write like finite expressions? You cannot write this in Lambda Calculus because we mentioned factorial, and in this expression we don't know what factorial is. Well, we can define like subtraction, but I'm not going there. But subtraction can be also defined in piano. But this one will not work in Lambda. We need a way to pass something into like disclosing to some combinator to produce stuff. So Y combinator will help to produce that. So if you see like here, it's a little bit like simpler than here, because this one here applies to X, and X here is for laziness. I believe like in JavaScript you have some ways to define lazy stuff like just arrow or like parentheses and then arrow. But I'm not a JavaScript programmer. Last time I did JavaScript was like 15 years ago. So I mean, like, and then later I learned this new, like, very beautiful notation. So I enjoy it more, but still, like, it's not my practical language. So that's how it is. We just throw in X for laziness. And to build a factorial, we define a factorial as Y combinator applied to factorial gen. And then, like, it will be a function that will take a factorial. Like, factorial gen is something that takes a function, takes a number, and if the number is 0, we return 1. Otherwise, we multiply that n by this function applied to n minus 1. And so we can do this, and basically I can show you how. Like, it works. Yeah, this is a factorial of 20. We could throw in more, but like it will be still like Stack Overflow, so we can try this. 30 and no, it does, but it's not an integer number, so you see it works. And basically you can, like, because we have conditionals, we have numbers, we have like the integer operations, so through, from natural numbers we can define integer numbers, we can define rationals, and we can go ahead like and build the whole arithmetics, and then through recursion we can define loops. And basically, we can implement anything here, except maybe like alert. For alert, we'll have to go like outside. And here, I also had to write like regular JavaScript multiplication and regular expression, because otherwise the expression would be not too beautiful and really hard to decipher. So here are the references, like interesting reading. Well, not everything, but yeah, a lot of interesting stuff. And questions? And before questions, I can also say that this book of mine is coming out soon at Artima, so this topic is also covered there. This diagram is wrong. Anything? So I'm done. Thank you.